Hello Nidir, long time to make a video. Uh, but yeah, okay, we'll do this. We'll start with chemistry and we'll like slowly kind of work our way through the rest of the stuff, like in chemistry, like AS level and A level. We'll start with something a little bit smaller, like the lattice energy, and then go on to I guess, the longer chapters so that it is a little bit of a revision. We'll start with chapter 19. We have not done this before, so we'll see how much we can do. Maybe I might split this into two videos, but let's see. Might just cover it in one video. Okay. So let's talk about what. Uh, so this chapter is all about enthalpies, energies, and like that's on the measurement side, like what we are measuring, which is the energies, and the lattice itself, right? So like, what does lattice and energy mean, right? Like those are the two chapters, those two parts of the chapter, so to speak. So let's just quickly revise what lattice means. Lattice basically, like if you think about a lattice say of anything, right? Like say you talk about NaCl lattice, right? Like so they say that it looks like this, right? Like what? So the gray ones here are sodium atoms and the green ones here are chlorine atoms. So if you look at it, this is a sodium atom, and on each side it is on six um, sides it is surrounded by another chlorine. So each of these gray, imagine that this is repeated, right, in all directions, in all three directions. So you can imagine that each gray is surrounded by six chlorine atoms, and each chlorine atom is surrounded by six gray atoms in turn, right, and one outside the paper. So this is what a lattice means. Lattice means that say a periodic arrangement, right, of positive and negative ions together, right? So that is what a lattice means. So let's try to understand what we are trying to understand in this chapter. Uh, so we start with what they call a lattice energy, right? And we want to understand this one first, right? So let's read through the book here a little bit. Again, for this chapter, I will recommend for chemistry in general, but the book is written very smoothly, like in the sense it takes you step by step through logic. So specifically for physical chemistry, it's always recommended to go through the book completely because whatever you need to know is given in the book. There is no trickery, there is no like trick questions. Everything comes on the book, right? Okay, that said, let's come back. So we want to start from defining lattice energy and work our way up from there, right? So it says when atoms combine, when ions, right, not atoms, ions, right, ions combine to form an ionic solid, there is a huge release of energy, right? So let's understand what this is. So ions are like, say in our case, sodium chloride, like salt example. So sodium plus Na plus. So Na plus is an ion. Cl minus is also an ion. So when they combine to form an ionic solid, which is an ionic solid, is basically these ions arranged in a lattice form. And when they are arranged in a lattice form, it becomes a solid, right? Like so, the salt that you get in the market is an ionic solid. It is Na and Cl arranged in a lattice form, as we saw. Like each chlorine is surrounded by six of those Na, right? So because each chlorine is surrounded by 6 Na and each Na is surrounded by 6 chlorine, which is why the formula is NaCl, not NaCl2 or Na2Cl, right? Because the thing is same. But if you say search for something more tricky, say something like CaCl2 lattice structure, CaCl2 lattice structure, then you will see that it is unequal. Like in the sense, a chlorine, one calcium is surrounded by maybe six chlorine, but that's not true for other way. Like this is may not be 100% accurate, but kind of difficult to visualize. But each chlorine is surrounded by say six calciums, but then each calcium will be surrounded by only three chlorines, something like that. Like the ratio will be off. Anyway, all that is a deviation a little bit, but I'm just trying to give you context here. So when you arrange ions, right, you start with Ca plus and Cl2 minus, Cl minus, and then you combine them in a lattice, or Na plus and Cl minus, and you combine them in a lattice, then the huge release of energy, because now the positive ions and the negative ions are very close to each other, right? So that when they're close to each other and positive and negative like to be close to another, so there'll be a huge release of energy, right? So that's what they're talking about here. The reaction is highly exothermic. Exothermic is release of energy, right? The energy given out when ions of positive charges come together to form crystalline lattice, right, is called the lattice energy. I hope you understand all of this. So lattice energy is the enthalpy change when 1 mole of ionic compound is formed from its gaseous condition under standard condition. So let's just write it here because this is the most important thing. So again, standard conditions in enthalpy or energy, we always talk about this. So enthalpy. So this is the enthalpy when 1 mole of gaseous ions, right, form, say, like form an ionic solid under standard conditions, right? Right, this is all standard wording. So the important part is you start off as gaseous ions. So you start off as, say, Na plus, which is gas, right? Gaseous ions, and then Cl minus, which is gas, and maybe you'll need two of those, right? To form NaCl, which is a solid, right? So you start from gaseous ions and form an ionic solid, right? Which is like a lattice. Uh, so this one is a lattice, right? Maybe we can write it like this. This one is in a lattice form. And of course, everything else is just standard. So you want to form 1 mole finally of this. So this number needs to be 1. So whatever you need to take from here, then you take it accordingly, right? Uh, okay. Yeah, my balancing number I did not notice or incorrect. So 1 mole here. Again, similarly here, if you want to form 1 mole here, 1 mole and Cl2 here is wrong. It should be underneath here. But you start off, the important highlight items are gaseous ions, right? Gaseous ions, and then finally you're forming 1 mole of ionic solid, right? And of course, standard condition and all is like just things that to say, right? So the question is how much delta H, right, or enthalpy change is released in this process. This is what we call lattice energy, right? So the direction is from gas to solid. No, okay. So another quick note about why we call it enthalpy and not energy. So if you remember from last chapter, so whenever you supply the heat, like energy, right? Like, so if you remember, work done is Q, that is equal to U plus P delta V, right? So in a way, enthalpy is related to the amount of heat that you give, and energy is kind of like an internal energy change, right? That's what we used to say in a gas way. Like this is generally true for gases, right? That's what we talked about. So this is like the amount of work done on the gas, right? So we used to talk like that. So now here the thing is, because you are making a solid, right? At the end of the day, the change in volume is very less, right? So this factor is usually like we ignore it for like solid conversions and all of that, because change of volume for solids is like difficult to measure. In gas, it's like okay, like I reduced 10% of the volume, right? Something like that. For a solid, because they generally exist as a, like imagine that if you keep 1 grain of uh, 1 cube of salt in a room and 1 cube of salt in a glass, it is still 1 cube of salt, right? Like the volume, it is the same. So in a way, change of volume is difficult to measure. So we say that energy or enthalpy here is like similar. Like so, enthalpy is usually this, and it changes it, but we say that this we can ignore in this case. So just a quick note about that. So we don't bother about energy or enthalpy here, as we would do in gases. Okay, just erasing that part out because that's just a side point. Okay. Okay, so let's move on. Let's see what else the book has to tell us about this. So, few things to observe, right? So, first thing it says it is the gaseous ions that combine to form an ionic solid, and they are saying that the lattice energy is always exothermic, right? So, if you take gaseous atoms, that gaseous ions who want to come together, right? Because there are pluses and minuses in the air, and if you make them a solid, make them a lattice. Alright, that is always a good thing. So good thing as in good thing for the atoms, and if it's a good thing for the atoms, then they show their happiness or whatever by coming in a lower energy state. So that means they release the energy, right? So that is exothermic. So lattice energy is always exothermic. Like the more you will like just understand these logically, you don't have to remember what is exothermic and what is endothermic, right? Okay. So as a result, whenever we have exothermic, delta H of lattice, right? Like the way we write it like that is always negative, right? Okay. Feel free to go through the book for the this thing. But we'll go through like the main points, and then we can cover the rest when you read and come back with doubts. Okay. So then they talk about that there's no direct way to measure. There is something called the Born-Haber cycle through which you measure this delta H for any solid or any group of atom. Like NaCl, say you want to measure this number minus 787 minus 2500, right? Like you want to measure this. So it says for 1 mole, if you want to make for MgCl2, then you want to create, then it releases 2526 kilojoules of energy, right? Okay. Yeah, so we'll just go through things in detail slowly. So this is the rough introduction, right? Okay, so let's see. Let's before we get into how we find the lattice energy, which is through this Born-Haber cycle. Let's just talk about two other energies before, which is the enthalpy change for atomization and enthalpy change for or and electron affinity. Okay, so if you remember from last year, we talked about all kinds of enthalpy change, right? Like if you remember enthalpy change of this, enthalpy change of that, so enthalpy change of vaporization, enthalpy change of whatever. Like there are so many terms, right? I don't. It's not on top of my head right now, but like you have enthalpy change of basically everything, right? Like any process that can happen, any chemical change that can happen, you can have enthalpy change in it. So to speak, that if you say mix two things, right? If you dissolve anything in water, does the water get warm or does the water get cold, right? So that is something like which we'll talk about in this chapter. It can be called as enthalpy change of hydration or enthalpy change of solution, right? So we have to understand those, right? Because anything can be get warmer and can get colder because that's chemistry, right? Okay, so in this case, we have enthalpy change of atomization. So what it means is atomization is we are relating to this equation. So you start off as something which is solid, a pure metal that is solid, 1 mole of it, and then you convert it into gas. So basically, the idea is whenever anything is a solid, it is arranged as in this lattice form, right? Now you make them into gas, right? So each atom is kind of freely moving everywhere. So it has kind of from those molecules or whatever, like in the periodic arrangement, they have now become free, like in a gas. So they have now isolated atoms, right? This is a lithium matrix or a lithium lattice, and this is just free lithium atom. So which is why it's called atomization. So in this energy, of course, you can imagine that if something is solid, then to make it a gas, you have to heat it up, right? You have to make it move like water. You boil, right? So which is why these energies are always positive, right? Like so to convert anything from solid to gas or something that's already gas, right? Something like chlorine, to convert it into atoms of chlorine, right? You'll always have to give an energy, right? Because you're breaking something that's naturally existing. So which is what they're saying there always. So that's one thing, right? Okay. Other thing that we want to talk about is electron affinity. So electron affinity, so let me talk about it here, is the opposite of ionization energy. So if you remember from last year, uh, so what we're talking about here is electron affinity or EA. And last year or like previously when we talked about chemistry, we talked about ionization energy, right? So if you remember ionization energy, IE, is the amount of energy you need to take out one electron from the outermost shell, right? That is the amount of energy you'll have to give. So imagine you have the Na atom, which is right now neutral, right? But we know that the way it is structured right now is 2881, right? So it ideally wants to lose that one extra electron to make it a complete stable orbit. But the problem is right now it is neutral, right? As soon as you pull an electron out of this, right? pull an electron out of this, and so you leave a positive charge, right? So these are so you have 17 protons in the nucleus, and outside you have, this is first shell, this second shell, this is third shell, and this is fourth shell. It loses that electron, right, from the outermost shell. So as a result, now it only has 16 electrons, right? So which is why it has a plus charge. Uh, so even though it is more stable, quote unquote, you still have to give in energy, right? To you still like, so this energy, whatever you basically give or take here, basically you have to always give this energy. So ionization energy will be so if you say the delta H of this reaction, right? Ionization enthalpy or ionization energy in this case, because you have to give an energy, so it will be positive, right? So just keep that in mind, right? Like it makes sense. So you're giving an energy, it is endothermic, or you have to supply energy to the system, right? So ionization energy is the opposite of this. Ionization energy, sorry, electron affinity is the opposite of this. In electron affinity, you say that instead of removing electrons, I'm adding electrons, right? So you don't add electrons in, of course, Na, right? You add some in something that is, say, 2887, right? Which is chlorine. And chlorine always wants one more electron to go, right? And now it has one extra electron. So it becomes chlorine minus, right? So this in this case, delta H will be negative, right? So this is, oh, so what it means is it likes it. This reaction is exothermic, right? So it likes it. It wants that extra electron, and it is happy, and it gives you energy as a return. Here in this case, you are pushing, keeping, like tearing an electron, an atom apart, right? So you give in energy, which is why this is endothermic, right? Okay. So this, so if, because you are adding the first electron, this is called EA1, right? Similarly, we have ionization energy 1, ionization energy 2. Similarly, here we have EA1, EA2. So imagine if something, you start with oxygen, right? You pull off an electron, right? It likes it. It has 2, 8, like it in the outermost electron it has 6, right? So now it has become 7, and then this minus 1, you add another this one. So this is, first one is EA1, second one is EA2. So to this minus 1, you add another one, so it becomes O2 minus, which it also likes, because now it has become from 7 in the outermost shell, valence shell, to the 8, right? Now it has a complete shell, and it really likes that, right? So to convert, so this is what we call electron affinity, right? This is kind of like the opposite of ionization energy in a way, right? So this is what we call electron affinity. So this is important. Okay, now that we understand both atomization and this thing, another thing is always to understand the trends, right? So let's see if they talk about trends now. So let's see what it talks about here. So we have understood. You feel free to again go through the book here, but it says when the, yeah. So here the trend is, okay. One trend that I forgot to tell you here. So the first electron affinity is usually negative. Negative is good, right? So that means it likes to give out energy, and it becomes O minus. But the second electron now that you're adding, the thing that it likes it, but the problem is it is already charged, right? And to a negative charge body, you are again pushing one more electron inside it. So it does not like that aspect. It likes the fact that it is complete shell, but it doesn't like the fact that you're pushing an electron inside, like a negative repulsion, right? So which is why the second electron affinity, EA2, will be positive. It doesn't like that, right? So net to add both the electrons, it will be minus of the first one and positive of the second one, right? Like you just add the two numbers up. So you get that overall, to make O gas into O2 minus, you will have to supply energy, right? Because it is positive. Okay. Another thing in chemistry is always to understand the trends, right? Like you need to understand how things move. And of course, in chemistry, so it's the same with electron affinity also. The trends are not exactly clear, and the data is way less, much less data is available as compared to electron ionization energy, comparatively. So in this case, say you take this second period here, right? This one. chlorine, nitrogen, oxygen, fluorine, right here in the second period, right? So we see that electron affinity here is negative, then it becomes zero, then it becomes then it becomes negative, and then it becomes more negative, right? So it goes. So here we see that the trend here is not very clear. So let's see what it is saying here. Okay, so before we get into the trends, let's just understand what we are trying to do here, right? We are trying to push in electrons into an atom, right? And we are pushing electron in one at a time, right? And the question is, how uh, will the atom like it or not? So one thing that is obvious is the factors that are here, right? So if there is more nuclear charge, right, in the nucleus itself, and if you're trying to push an electron in, then it will like that. If there's a lot of positive charge and you're pushing an electron in, then it will like that. So the more the nuclear charge, the better the more it will like, right? So the higher will be the negative aspect of the electron affinity. That's number one. Number two is the radius of the atom. So if the radius is bigger and then you're bringing an electron in, then it will be tougher for the nucleus to pull on that electron, and which is why the electron affinity it won't like as much, right? So and the last thing is what we call shielding, right? So if there are so the positive nucleus is here, and then there is an electron cloud in the middle, right? And then you're trying to add electron in the valence shell, in the outermost shell, but there are electrons in the middle. So they do what we call shielding. So even though there is a lot of positive charge, but that's cancelled by a lot of negative charge around it. So it's not able to see the internal big positive charge because of the shielding of electrons that are present here, right? So where there is high amount of shielding, um, it is not good for the electron affinity, right? Because because the nucleus, the positive nucleus, is not able to pull on the electrons. So these are the three factors. On these three factors, now let's look at this chart. So if you look at this oxygen group here, oxygen, sulfur, selenium, and telluride, right? It looks like it's minus 41, so it is good. This it likes, but then it likes a little bit less, and then maybe likes a little bit less, right? Let's see the other group. It looks like this one, then it starts to, okay, maybe not like as much, and maybe not like as much. So this, what they say here is there is no clear pattern down the groups for that much, but across the period, if you see, this is minus 140, minus 122, minus 141, minus 328. If you ignore the nitrogen for now, it looks like it is becoming more and more and more negative, right? So that means it is really liking that. So that's good, right? So that goes on to say it is very, if you add an electron in fluorine, it will really like it as compared to if you add an electron in carbon, right? Uh, so this can be arranged. This can be answered through the further away factor, right? Because if you see across the period, the size of the atom shrinks, right? Please remember the trends. So fluorine will be smaller than carbon. So the pull, right, of the nucleus that the on the electron will be much higher in fluorine, which is why this thing is there, right? So you might say that, okay, down the group, why is there no clear trend? So if we analyze this, then the nuclear charge is increasing, right? There is much and bigger and bigger amount of protons that the iodine has as compared to fluorine. But the thing is, there are also so many electrons to shield the effect of those positive this thing. So we don't know. Okay, there are two factors, and we need to understand which one goes stronger. So there's no clear trend in such thing. But from left to right, we see a clear trend that the atom is getting smaller and smaller and smaller. So it gets easier, right? Why is nitrogen an exception here? That is something we can discuss maybe if it comes up, but for now you can ignore it. Okay, uh, so let's move on, right? So now that we understand both electron affinity and atomization, now we have enough to come back, right, to what we started this chapter as the lattice energy. So we said that the way we understand lattice energy is through what we call Born-Haber cycle. Let me take this Born-Haber cycle here. Take it with this thing. Right. So if you remember, we had studied something called Hess's law, right? Uh, so in thermo in this one enthalpies and like last year's chapter. So Hess's law is basically we try to create three different states, right? And we try to draw arrows from one state to the other, right? So if say you have ions in gaseous form, again remember, just a quick recap. We are trying to do in lattice energy. We have gaseous atoms, gaseous ions, clarification, right? To ionic solid, right? So we have ions in the gaseous state, so that is this guy right here, right? So number one is number one here. Both of these are number one, right? And then we this is called lattice energy, and then we are forming the ionic compound, right? So let's call this number two here. So this is number two. But they are saying because we can't know this energy, this what we call delta H lattice directly. So we what we try to do is try to go through a secondary state, right? And then come back to this one. So what is that secondary state? They say just atoms in their standard elements in their standard state. So maybe if it sodium exists as a solid, right? And chlorine naturally exists as Cl2 but in a gaseous state, right? Where we need Cl minus. So atoms and ions, right? So there is a difference. So these are atoms, they are molecules. Molecules become atoms, and atom becomes ion, right? So so that is what they call like. So maybe if we can figure out. So okay, we don't know this guy, right? We want to figure out this guy. So what they always say in Hess cycle is think about an intermediate state, right? And then think about if you know these two energies. So if you remember from last year, this Na solid plus Cl2 gas. I'm just writing what I've written there to NaCl solid. Like so, this arrow, right? So this is what, by definition, what we call enthalpy change of formation. So this you generally know. So the idea is you take things in their natural state. You take an atom of this thing, take an atom, and control it in this thing. Observe the change in temperature when it happens, and once you know the change in temperature, then you can figure out how much energy was released in this formation of NaCl solid. Right. So this can be measured experimentally. Right. So the question is now, how do we understand? So one side is clear, right? So but the question is, how do we find this guy? So let's in your book they call it delta H1. So let's try to understand how to go from here to here, right? So look at what H1 we are doing. So we are trying to create Na plus gas, right, and Cl minus gas. And what we start off as is Na solid. I'm trying to draw the opposite of this arrow, so not downwards but upwards. That's okay. Like you can think about that does not matter quite a lot, like the arrow, because it's just swapping the arrow is just swapping the sign. And you start with Cl2 gas, right? So these are the two inputs, which is this guy right here, the elements in the standard form. And what you need is ionized gaseous atoms, right? Like or ion or gaseous ions directly, simply, right? So you want to do this. So so if you observe what you're trying to do here, this is delta H1, and here this is delta H formation, right? So in delta H1 reaction, what you want is you do a four-step thing, right? So first you atomize the metal atom, right? So you convert this into Na gas in a way, right? Then you ionize the metal. That means you convert Na gas into Na plus gas, right? Which are ions. Then the next thing you do is atomize the non-metal, right? So you convert Cl2 gas, right, into Cl gas molecules. So this is what we studied as atomization, right? Right now in the previous chapter, previous section. And then you finally ionize this non-metal, right? So the reaction here is the gas that you have produced here. You add electrons to it. You create Cl minus as the gaseous atoms, right? So this is exactly just to connect things back. So this is the exactly electron affinity, the reaction that we learned, and this is the atomization thing that we saw. This is also atomization in the way, right, from what we saw. and here in this case you have to convert. In the second case, we have to convert Na gas what you produce, and then you have to convert them into Na plus gas, and then you have to remove an electron out, right? So this is what, again, from last section what we saw it as, this is ionization energy. So if you say, like, do all the four things, right? Atomize the metal, right? Then ionize the metal, so you have gotten this product here. So you started from Na and got Na plus gas. Then you look at non-metal, you atomize the non-metal, and then ionize the non-metal. So you get finally this one, right? There it might be a way. There might be a case where there is an Mg2 plus here. In that case, right? Like say you started with Mg as a solid and say a Cl2 as a gas. In that case, you might require Mg2 plus and chlorine minus here on both in gaseous forms. In that case, you will have to ionize Mg twice, right? So first you atomize Mg. So in that case, you start with Mg solid, convert it into Mg gas. Once you have converted into Mg gas, you convert it into Mg plus a gas. Sorry, I'm writing solid but saying gas. Mg plus gas, right? And then you convert it into Mg2 plus gas. And that is when you do, so this is step 1 here, right? Which you, when you atomize things, so you convert it into free atoms, which are these gaseous atoms. Then you ionize the metal, right? So this is step 1. So you have converted from Mg stable to Mg plus, and then you again ionize. So this is also step 2, but the first one is ionization energy 1, second one is ionization energy 2, right? So to get to what you want, basically. So atomize, right? Similarly, you might need 2 electron affinities here and not just one, right? So this way we can figure out what H1 is if we do these 4 steps. And now that we know H1 and HF, then we can figure out what this H lattice is. Does that make a little bit of sense? Feel free to rewind the video and kind of think about this again. One very helpful way to understand this is what your book does, which is to what we call make an energy. Let me take your book's help from here. Yeah, so like we can maybe discuss through an example. I will come to what I was referring to. Let's just cover this example first. Right. So in this example, if you see, give me a second, it is appearing here. Yeah. So if you see, these are again the 4 steps, right? So these are gas ions here, right, on the top. Then this is items in their standard states, right? Elements in their standard states. And then this is finally the ionic solid that you need. Right? You can always convert the atoms in their standard states to ionic solid directly. That we always call formation, right? Delta H of formation. So this is known. But what you want to find is from gaseous atoms, gaseous ions to this one. So that is what we call H lattice, right? That is what we are interested in finding. So the process is through what we call H1, right? So that is again, so to convert lithium solid to lithium gas first, don't touch the fluorine. Then convert lithium gas to lithium plus gas, right? Which is ionize the metal. So these are all metal steps, right? Then you start with the fluorine. So fluorine, then you add, because this is already a gas. So first thing that you do is, sorry, not this one. So first thing that you do is convert F2 into F gas, right? So this is ionization here, right? This step right here. Sorry, atomization here, and then finally you ionize that thing, ionize the non-metal. So these 2 steps here are non-metal steps, right? So once you know all the 4 steps here, 1, 2, 3, 4, that then you can figure out what H1 is, and then you also figure out what HF is, and then finally this is the golden crown jewel, right, that you're trying to figure out. So eyes on the prize. Okay. We understand this. So now what I was saying was that would be an helpful thing. So all of these energies in a way are given to you. So let's try to go through these steps. Given to you, or they'll be stated in the question in some way. So first thing is atomization of lithium, right? So that can be measured, that can be understood. So that is what they have given to you as plus 161. So that means you'll have to give in energy. Plus means give in energy, right? So you have to convert something from solid to gas. You'll of course have to give energy. right? Then you convert lithium into lithium plus. Sorry, yeah, this should be a lithium plus. I don't know, they've forgotten a plus sign here. So this is a lithium plus here, which is step number 2, right? An ion. In this also you have to give an energy, right? Because you're trying to make a neutral atom into a positive charged atom now, positive charged ion, right? So you're trying to create charges. That's always going to be tough. So both of the times, so atomization and then IE1, you're given energy. Then in the second, and then you focus towards the non-metal. So you convert again F2, which is standard state, is a gas, to F single atom, that's a gas. So you have to give atomization energy or separating FF out, right, from here, and like breaking an FF bond, right? So you have to give some energy for that. And then finally, the free gaseous atom, you now you have to make it an F minus. Now, but in this case, you get energy back, right? It releases, it is happy to get that electron. It likes it. So the first electron enthalpy, electron affinity is generally seen to be negative, right? Like, so it gives energy out. So this is, and then we add all of these up, right? So tuck tuck plus plus plus, and then the last one is minus. You get 432. And then also in the question is given, it is given to you that lattice energy of formation directly is 670. Then you just see whatever you get, and finally you get this number. Taking into account the signs, right? So make sure you correspond those signs with what you see here and try to like redo this calculation, right? Okay. So what I was saying, what a helpful this thing is, what they call an energy level diagram. So let's try to understand this a little bit. This is a helpful sort of visualization. Um, so it's very similar in a way, but here, uh, so you start from again. It's the same thing. I just shown it in a different form. So you see that there is step one, right here. So that means you must have started this in natural states here, right? Elements in natural state, which is solid and gas, right? What do you know? Metals generally are solid outside, and this is gas. First thing that you do is convert from solid to gas. So give energy, right? Giving energy means taking it to a higher energy state. So giving energy, right? Then you again make lithium to lithium plus. Again, give a lot of energy. So this energy here is, this step here is IE1, right? Right here. First step was delta H atomization, right? Then this is IE1. Then you convert, step 3 is delta H of atomization, but for fluorine this time, right? But delta H, now EA1 is not more positive because you get some energy out. So that's good for you, right? That is EA1 right here. So you get some energy out. So the delta H here, in this case, it is negative, right? So you get some energy out. And then finally, what you need to do here is to get to this state, which is ionic solid, right? LIF, which is an ionic solid. So in this case, so what you need to find is when the gaseous ions to this, right? This is the transition that we call H lattice, right? What you know is natural state to ionic solid, which is H formation, right? And you know all these intermediate steps. So the idea now you can see from here very clearly that delta H lattice, right, which is this guy right here, right, this guy right here, right. So you can figure that out, right? It's like an equation. So you know that is a downward sign, right? You can convert this into this thing, and then you can add these up, and that must be equal to the sum of these guys, right? And then this will form an equation, and then you can figure out things from it. So if it's more helpful to visualize things as up arrows and down arrows, I highly recommend. This is something that I do. Like, you think like this, it is much easier. So this is what you call an energy level diagram, because there are levels of energy, right? So you either go down, go up in energy. If you are pushing energy into the system, so it's endothermic, right? Higher energy, higher energy, higher energy. And when you get energy out of the system, it is exothermic. So things just fall underneath. So this is the exothermic part, right? And then it will also be exothermic, right? For the gaseous ions to become an ionic solid, as we talked about, right? These are plus positive charged ions traveling as gaseous, right? They would love to be together, because pluses and minuses love to be together, right? In a nice patterned form where every lithium is satisfied with fluorines and every fluorine is satisfied by lithiums, right? So this is good. This part is good, right? Which is why it's a big negative enthalpy, and yeah, enthalpy change. Okay. And but at the same time, formation might be sometimes positive, might be sometimes negative. We don't know. Okay. So the idea is this is the Hess cycle, right? In a way, like all of this comes from what we call the Hess cycle, which is to go from step A to step B, but to find an intermediate step C, right? Like so, in this case, we want to find from here to here, but we see that okay, maybe this can be our intermediate step. So we figure out how to go to that intermediate step and to come out of that intermediate step, right? Which is C and B here. And then once you know both of those, then we can figure out what A to B. So this is the basic idea behind Hess cycle. Right? I highly recommend, like, and you have to, you should do some questions in this regard, right? We are not discussing questions right now, but there are some very good examples given here. There is a section where they say that this is extension work. I would leave you to read through this and understand. It is a small thing. Basically, the idea is they don't give you questions where there are three ionization energies. So Al to Al gas, then Al plus gas, then Al2 plus gas, then Al3 plus gas. So you have to ionize thrice here, right? So they just say that in CIE you won't get questions where you all have to ionize three times. But say questions like Mg, where you have to convert atomization, then IE1, IE2, and then finally you start with the non-metal after that, which is chlorine. So those things can come. Okay, so very important to kind of understand this as well. So make sure you go through these questions and then this is that. So basic thing, right? So this is the idea. Once you are able to do this, you will be able to crack questions. But that's not what chemistry is about. Chemistry is all about understanding trends, understanding if say this magnesium chloride, magnesium is swapped with some other element, right? Say from the same group. So what should I see? Uh, should I see a higher lattice enthalpy change? Should I see a lower lattice enthalpy change, right? So for or lattice energy change, right? So the idea is to understand what lattice enthalpy, lattice energy depends on. So let's try to see. They are fairly simple questions in chemistry, but fairly common. So understand, right? Like what is a lattice, right? Lattice is this regular periodic arrangement of sodiums and chlorines around sodium, right? So the thing is, if there is a good match of size, right? So understand if there are small size and both the Na and the chlorine are small, right? So they can be arranged that this arrangement of one atom and six around it, like two here, two here, two here, right, can be easily be achieved. Imagine if this one was bigger, right? And then these ones were smaller, right? So the non-metal is small, but this is big. So it's like you play smaller balls around a big ball. That's not really very good because okay, this big atom is nicely surrounded by six atoms, but this small atom is now also has to be surrounded by six big atoms, right, on this side, which is kind of tough, right? So good match between a non-metal and a metal, the relative size should be similar. Okay, so that's key number one, to have good lattice formation. So good lattice, again, if they are happy, then they will release, then that drop here will be very high, this drop, right? If they like it, then it will be good. Like here the drop is massive, right? So that means magnesium and chlorine size must be similar. Okay, so that's one thing. Other thing that we want to compare is, say, okay, I take two things of similar size, but now they are both smaller, right? So earlier what we were discussing is one small, one big, or one small, one big, right? That's not good. Now I'm saying both are same size, but both are smaller or both are bigger. Which is better? So the again, it's all about how things fit in a lattice, right? Now if you are able to fit things in a lattice, right? So if now things are smaller, now you can put a nice tight lattice you can make. Everything will be small, right? So and small is good because positive likes to be near negative. So if you can place them very close because the size of the atoms themselves is small, they love it, right? So in this case, so we what we understand is both small and both of same size is the best scenario. Both big and one big and one small is the worst combination. So that is the trend that we see here as well. So if you take a small metal with a small non-metal, you get a lot of energy out. So lattice enthalpy is very high, lattice energy is very high. It releases a lot of energy. But if you take cesium and then say an iodine, that's bad, right? So the match, like these are both big, right? And they don't like it that much. Um, so that is another point, right? So the size of the atom increase, it becomes less and less exothermic, right? Then another thing is for the same charge, right? One we talked about is size match. One we talked about is the difference in like like big and small, right? Both of them. Okay. The third factor that they talk about is if there is a same atom, right? Same charge, sorry. So Li plus, Na plus, K plus, rubium plus, and cesium plus. Between them, so this is a lot down the period. So if you see here, so this is this period. So this period right here, Li, Na, K, rubium, and cesium. So if you go down the period, right, but you single have a single plus charge, then that whole plus charge is distributed along a much bigger radius, right? Because it's now much down the this thing. So it's like a big atom. So this what they call a density, charge density is very low. So here this plus charge is on a small nice lithium atom, and this plus charge here is on a nice big cesium atom. So that's not good. So lithium will be better, right, for ionic lattice matching. Again, so that's what they talk about here. Again, these are fairly obvious point, nothing counterintuitive here, but you have to understand how what factors affect lattice size. So just again read through the book. Once you understand it, you understand it. Okay. Another thing, last thing. Now this might be a little bit tricky. Is if there is a positive ion, right? So there is. So imagine how what we told is there is a uh, sodium in the middle, and then the chlorines around it, right? Now if you have a thing that is a very small atom like a lithium, and then you have a fluorine or a chlorine or an iodine or even a bromine, which is a huge this thing next to it. Now the thing is, if there is a iodine, right, it's huge, and then there's a fluorine which is small. So if you place a nice strong positive charge, which is like a lithium, small positive charge, right, plus one, what versus so that positive charge will now pull the electron cloud towards itself. If it's a big atom like iodine, it will be able to pull like some of the electron cloud towards itself. So this is what we call polarization. So the electron cloud actually is iodines, right? But it's able to get pulled by the positive charge. So this is easily able to happen when there is a size mismatch. When there is a lithium here and an iodine there. In that case, if you think about it, this is kind of like a covalent bond, right? Like covalent bond, where there is sharing of electrons, right? With the electron clouds merge. In that case, so this even though we started as what we call an ionic bond, right? Like a lithium and a chlorine, an Li plus, which is this thing, and an I minus, right? Which is a big negative charge. So they should have positive, negative this thing. But so that is what we call an ions, right? So that they form what we call an ionic bond. But when there is some sharing of electron cloud, right? Electron cloud kind of goes around both the atoms, then that is what we call covalent behavior. So so this adds to covalent behavior. This such kind of a thing, like a small, nice positive charge with a small positive charge with a big negative charge, it adds to covalent behavior. It's like, oh, I'm now like kind of sharing your own electron cloud, and it's like so ionic bond kind of changes into covalent bond in this case. So again, so it depends. So what it matters is the charge density of the cation. So if cation is small, cation has a high charge, that's good. Cation is the positive charge. Anion or the negative charge is large, and it has a large negative charge, that's bad. That's bad for the electron cloud. So it gets pulled, right? That's what they're talking about here. Feel free to again go through the book. Okay. So the last thing that they talk about here is okay. Yeah, thermal stability of carbonates here. So this is a little bit of a deviation. So let's just kind of like start afresh here. So we are going to talk about group 2 carbonates and nitrates and their thermal stability. So this is a little bit of a digression, but we'll come back to this. Like in the sense, we'll do it now, but we'll come back to our main topic of discussion. Uh, okay, so first of all, take a break here, right? Like try to understand things, go through it slowly, go through the book, right? Try to understand that you understand lattice energy properly. Okay, once you do that, you're sure about, let's move on to the second half of the chapter, which is this one. Okay. So this is group 2 carbonates and nitrates, right? And we are trying to understand the thermal stability. So group 2 here, so group always goes down. It starts from beryllium, magnesium, calcium, strontium, barium, and we are trying to form carbonates. So carbonates is CaCO3, right? One of the examples is CaCO3. And what you're trying is identifying the thermal stability. So thermal stability is, that means you will heat it at some point. And the idea is whenever you heat a carbonate, you always get carbon dioxide out and you form an oxide, right? So the idea is you're trying to understand the thermal stability of such things. So if you are comparing magnesium carbonate to calcium carbonate to strontium carbonate and to barium carbonate, amongst these four, which will be easily be likely to break, right? So one of the easy ways to understand it, at what temperature does it break. So this one breaks at 540, this one breaks at 1360. That means you'll have to heat this a lot more. So that means barium carbonate is more stable, right? So in enthalpy words, it becomes the same as plus, right? So you're supplying energy. So here you have to supply a lot more energy, and here you have to supply less energy, right? Same thing. It's the same kind of a thing. Okay. So the idea is we want to understand why this is the case. So we can understand this through this polarization that we talked about. So now think that there is a magnesium carbonate, right? Magnesium is small atom. Barium is huge atom, right? So if you want to distort the big carbonate is a big electron cloud, right? And which one will be able to distort the electron cloud more? The smaller magnesium atom, right? So that means it takes the electrons from carbonate and pulls it towards itself easily. Once it does that, the bond, so you have to ultimately break out CO2, right? So if you create a weakness here, right? Like if you take their electrons, then they're more likely to kind of leave out, right? Just leave the one oxygen that it wants to be associated with calcium or magnesium in our case, and just leave, like leave with the other atoms. So it's easier for them. If you take some of their electrons, then it becomes easier for the far end in a way to detach itself from the atom. Which is why barium carbonate is very stable because it does not polarize the carbonate cloud that much. Once it doesn't do that, it can't break away as freely as compared to magnesium carbonate, in which magnesium pulls the electron cloud toward itself, breaking that CO2 bond, and it can just go away. So this is what they talk about here, that the greater the polarization of the carbonate ion, the easier it is to weaken the carbon oxygen bond in the carbonate and form carbon dioxide. So just understand this sentence, go through it slowly, you'll understand. An exact similar thing happens in group 2 nitrates as well. So magnesium nitrate will be the least stable and barium nitrate will be the most stable, right? So similar logic. So make sure you understand this. Okay. Okay. So last part of the chapter is about enthalpy changes in a solution, right? Again, take a little bit of a break. It's a little bit of a change of things that we're talking about, uh, and start afresh. Okay. So we are moving towards the solution, right? So now we have a different sort of an environment. Earlier, so the first thing that we talked about was lattice energy, right? We were converted gaseous ions into lattice, uh, and which is a solid, right? And now what we are interested in is if we take this solid that we have made, right? And now we mix it in a solution. Mixed solution is water, right? You mix it in water. So the idea is what happens? Does the water get hot? Does the water get cold? Does the water stay the same temperature? So that is what, and usually things happen, right? So in say something like salt, right? Like you have to stir a little bit, so that means you have to put a little bit of energy in, so it's a little bit positive, right? Delta H there. But for other things, maybe they dissolve on their own, and when they dissolve, the thing gets heated up a little bit sometimes, right? Things happen. So this is what we call enthalpy change of solution. So right, so same thing. Is the energy absorbed or released when 1 mole of the ionic solid, right, dissolves in sufficient water to form a very dilute solution. So So say something like you say I start with MgCl2, which is solid, and then the aqueous is just a lot of water, and then you make MgCl2 aqueous, right? So let's just understand what is happening here. So what we're talking about is enthalpy change of solution now, right? So what we're talking about is we are starting with MgCl2, which is a solid, and we are converting it to MgCl2, which is what we call aqueous, right? So in aqueous, what happens is in a way the opposite of what we saw in lattice energy. So aqueous में मतलब basically there is like water, right? Water में Mg2 plus and Cl minus and Cl minus. There are two Cl minus here, right? They kind of become a little bit free, not as free as a gas, but they can like go around now. Like they become like their own thing, right? And the idea is from a strict lattice here, they become like relatively free ions, right? Not as free as gas, but not as tied down as a lattice also. Lattice is like a solid, like a fixed regular structure. Here they are again free, right? So the question here is so in this one, this is what we call delta H of solution, right? To convert anything from an ionic solid, right, to an aqueous form, delta H of solution, right? So in this case, sometimes you have to give energy to make them aqueous to, or like in a way, this is also in a way you can call this a solution, right? Like, so does it dissolve? Does it not dissolve, right? So this can also be understood if this delta H of solution is very positive, right? Very highly positive. That means you have to give a lot of energy. That means it is more like insoluble, right? Like you're putting something inside water, it is not dissolving, right? How much ever you stir. But if say delta H solution is a little bit positive, or even better, if the delta H solution is negative, right, then that means it is soluble, right? Maybe with a little bit of stirring, like in salt, right, NaCl, right? You little bit of stir, it goes away, or it is negative, that means it dissolves on its own. Sometimes that happens, right? Then it is good. So this is good. So this is a general like thumb rule, which your book also talks about. I'm generally covering whatever is in your book, so I'm not going well beyond that. Just FYI, so that you know what to remember and what not to remember. Right? So this is what they talk about here. Make you go through this experiment. I think it is a good practice for your this thing as well. Like it can come and it can come as a question also in your paper. Okay. So the idea is now this is solution, right? So this is solution. Now we have to understand a very close associated like brother enthalpy, which is called hydration, right? So let's try to understand what happens here, right? So solution, if you remember, uh, okay. So this is enthalpy change now of hydration. Now these are very close, solution and hydration. Now let's understand the difference between them. So hydration is basically this idea that H2O, right? H2O is not what we is not a flat atom. Like what I mean by that is it's not like one electron pair up, one electron pair up, and then one bond flat, right? It's instead like both the electron pair are on the top, and these two electron pairs push the bonded pair, the free electron pair push the bonded pair a little bit down, and it forms this kind of bent shape, right? This bent shape is very important because this bent shape creates a polarization. So the hydrogen, like oxygen, pulls the electron towards itself a little bit and pulls itself a little bit. And because it is not cancelling each other from positive to negative, right? So from positive to negative, from positive to negative, it creates a dipole moment, right? In this case, the dipole moments would cancel each other out. But here, because they are at an angle, there is a net dipole moment, right? That goes in this direction. So this bent water molecule creates a dipole moment, right? Or what makes a water molecule polar or a polar solvent. Okay, so this is the important part. Because it is polar, right? It has what you call like on oxygen a delta minus, and on hydrogens like a delta plus, like a little bit plus, because it's able to pull a little bit, and it's a little bit negative on this thing. Because of this, this negative and this positive is generated, right? Delta plus and delta minus. Now this positive and negative. Now, so imagine that this is that ionic solid, lattice of ions, right? This is what you're starting with. Now out comes a water molecule here, which is a little bit polar, and this negative atom pulls this positive atom a little bit, right? So you are kind of encouraging this positive atom to leave this lattice, right? It likes what it has right now. It likes the negative ions around it. It is very happy right now. But the outcomes this oxygen atom is like, I can also give you that stability that you need, right? I can also give you the negative charge that you need. So this one comes in and pulls a little bit, right? And see, like what happens eventually is that negative atom here comes out, right? And it is now quote unquote balanced, right? By four like four hydrogen atoms from two different water molecules, right? Like they are supplying the positive charge that it needs. Similarly, an positive charge here is there are four smaller water molecules around it, and these water molecules ka oxygen part, right? Hydrogen part is outside, right? So it surrounds the water molecule kind of surrounds each atom. So this is what we call kind of a solution forming, right? This is hydrating the molecule. So instead, so now this basically this positive ion, right, becomes free to come here, to come out of that thing, and now it can form like this association, and then it can go around the water molecule, like the water, this thing. So it's like the pile that it was earlier, like positive negative here, now it can go around with a bunch of smaller water molecules around it, and now it can freely travel in the solution. So this is what we call hydration. So again, how it is different from solution, we are just inching towards it, but the idea of hydration is to surround water molecules around an atom. So something like you start with a gaseous atom, right, which is or a, right, and then you convert it into an aqueous form of that ion, right? So not an atom, I think it is an ion only. You start off as a gaseous ion, yeah. So you start off as not an atom but a gaseous ion, right? And then you hydrate it. So so basically now it's a free atom. Gaseous ion just means like it is H plus but in a gas form, like just H plus, right? And but then you convert it into H plus or whatever. H plus is just an example. It can be Na or whatever in an aqueous form, right? So the idea is it is just an isolated atom, and now you are hydrating it, right? Surrounding it with water. So surrounding it with enough positive charges that it likes, or enough negative charges that it likes. So all of these are good things, right? So this energy, hydration energy, is good, right? Because there is only one ion involved. In solution, right, there is a positive and a negative, and we are considering both of them, right? So we'll talk about it. But one thing that you need to understand is there are only single isolated atom ion here, and once it's surrounded with aqueous things, it will like it. So that is good thing. That means delta H of hydration is always exothermic, right? So it will be negative. It likes it, right? No one wants to be an isolated positive charge. It wants to be an isolated. It wants to be a positive charge surrounded by negative delta negative charge of the water molecules, right? So so the now coming to how it is different from the solution ka hydration. So that is what we'll understand. Again, go through the book here to understand things. There are also trends given. Again, smaller radii, but a large charge is good. So depend. So you want to be able to predict between magnesium 2 plus and lithium plus, which will have more hydration energy. So again, think about some question like this. These are very important. Again, higher charge in small atoms will be good because it wants to pull electron from oxygen, right? So it's just stuff like that. Okay, so this is what I was talking about. So it is very important to understand the difference between solution and hydration enthalpy. So this is what this is about. So you start with gaseous ions, right? So gaseous ions is like, say you want to start with Na plus but in a gas form and Cl minus in a gas form. So this is something I've seen already, right? And you form NaCl in the solid form. So this, again, this is a transition that we know. This is what we call lattice energy. This we understand fully, and we saw how to calculate this previously. Now we are going one step further. We want to find NaCl in solid form needs to be converted into NaCl in aqueous form, right? So this is what we are interested in. Do we need to heat energy? Do we take NaCl solid and convert it in a liquid, right? Do you have to put energy in or put energy out? That is what we call delta energy, delta H of solution, right? This answer can be done through, now this is now your intermediate state, right? Now you solve this to the hydration energy. So you take each Na, right, and convert that into like an aqueous form, Na plus aqueous, and take a Cl and then convert it into Cl aqueous form, right? So these energies you know already. These are hydration enthalpies, and you know the lattice energy. So that can be used to find net total, right? So start from a solid, right, and then go to the aqueous form. So the idea in a way to understand this is something like, say if you have gaseous atoms that you started with, right, it has two choices that it can go. It can either form a lattice, right? The lattice matlab it has a nice regular structure with Cl balanced on all six sides, right? These are the four, and up and one down, right? On top of the page and below the page. So it likes that. That's good. So this energy will mostly be negative, right? It likes that. But it also can do one more thing, that Na plus can be surrounded by what we saw here, right? Something like this, right? Like a little bit, and that also it likes, right? So this is the hydration energy. So that also is negative. Now the question is, which does it like more, right? Does it like being more with chlorine, or does it like being more with, like, as a free atom with water molecules like this, right? So that relative difference, right? So this lattice energy minus, say, hydration energy determines the enthalpy of solution. So that determines its solubility, right? In a way, or its ability to dissolve. Does it like being stuck as a solid in the corner, or does it like being free inside the liquid solution? So that is what we call if it is soluble or not, right? So that's how we understand these things. So if you can calculate delta H, and if it's a little bit positive or negative, so then that is probably soluble. But if it's highly positive, right? So that means it likes to be in this form. That means its lattice energy is very high. It likes to really be with chlorine. Then it won't want to hydrate itself. Like this is low then in that case, right? Like maybe like this is the scenario we are creating. So then delta H will be very positive and not soluble, right? So this is the chart in a way of understanding solubility, hydration, and lattice energy altogether. So again, two of these will be given to you, and mostly these two are given to you, and you want to find the solubility for this thing. Feel free to go through the book here. Again, I'm not going through the examples, but the examples are everything here. Okay. The very last section of this thing is the solubility of group 2 sulfates, right? So again, similar thing here: magnesium, calcium, strontium, barium. And we have sulfates, and we are discussing which of these is the most soluble. So this is the data given to us. So how many moles can you dissolve in 1 decimeter, or 1 decimeter cube, or 1 decimeter cube is 1 liter of water? So you can dissolve very less, like 10 power minus, a very small amount here, and very high. So it looks like magnesium sulfate is the most soluble. Now the question is, why is it more soluble? So of course, so as we talked about, right, we are fighting two things here. We are fighting hydration enthalpy, and we are fighting lattice energy, right? So make sure, so you have to understand, right? Hydration enthalpy, we talked about that it is highest for this thing, right? Uh, and lowest for this thing, right? And we are also comparing now lattice energy, right? Lattice energy is how good it fits on a lattice. So in this case, right, magnesium and sulfate are both big. Sorry, magnesium is small, but sulfate is big. Here, this is big and big. But because this is too big and big, in a way, like sulfate is there in both. So that is what kind of dominates how much lattice satisfaction it gets, right? So in this format, it is located in a lattice, right? When it is surrounded by this. So if the size of the lattice, right, is determined by, say, chlorine is very big, then if you change Na size a little bit, then it really doesn't really matter. The amount of happiness that it gets in being in a lattice is determined by the spacing of Na and Cl, right? If Cl is huge and Na you change a little bit, then it doesn't really matter how much NH size changes, right? So what they tell here in this explanation is lattice energy doesn't really change from magnesium sulfate to this thing, but hydration enthalpy changes massively. Like this is very good, right? Because magnesium is small and it polarizes the O minus atoms, and barium, but it's big atom, so it can't polarizes the O atom. So hydration enthalpy for this is good. So the satisfaction that it gets in going through hydration is very high, right? But the satisfaction that barium gets is not very high, and the upper part doesn't really change for either of them. So of course, which one likes to dissolve will be the one that likes to release the hydration enthalpy, right? Hydration enthalpy is high. So because it likes to dissolve more, it likes to be hydrated more, it dissolves more, right? So the way that they fight, like write it as ki there are two competing factors, right? Hydration enthalpy and lattice energy, and the decrease is relatively large down the group for this hydration enthalpy, but for decrease in this is relatively smaller because of the large sulfate ion, right? Because now this is relatively like less changing, but this is changing a lot, so that means this will be the most soluble, which is what we see. Again, go through the book here. This is like the combination of all of the things that we saw in the chapter, but it's very important to understand what is happening here because this will definitely come 100% in your papers. Okay. Uh, yeah, so this is represented that in a energy level diagram, right? Like, so you start with gaseous atoms. One is hydration, where you hydrate each of those individual atoms, and one is lattice energy, where you convert it into this. So solution is kind of like this, and here this is hydration, and this is lattice, and then this is solution. So you see that hydration energy for calcium, which is much higher up, is very high, but lattice energy for this is low. Like so, hydration energy for this is low because this is a big atom, right? But this arrow has not changed as much because this is mostly determined by how big the sulfate atom is, right? So because this has decreased now a lot, so that means this arrow, the compensatory arrow, has become larger, right? So if it has become larger, then it has become more positive, so that means it will be less soluble. So strontium sulfate, right, will be less soluble than calcium sulfate. So again, same thing, but just given as a diagram. Okay. So solubility of group 2 sulfates decrease down the group. So this is something that you should remember as well and also know the logic of how this is coming. Okay. We'll stop here. Try to go through all the internal examples. Try to understand the chapter fully. It's very simple ideas, but you have to understand. The more work you put into it now, the easier it will be when you solve the papers. Okay, we'll stop here. Bye bye.